Hello my friends and welcome to this new practical activity on this time dimensionality reduction, which is not a branch of machine learning per se, but a very important technique to know how to handle when you work with big datasets, huge datasets with many features and for which you would like to reduce the complexity by reducing the dimensionality. And this is exactly what dimensionality reduction is about. So in this new part 9 dimensionality reduction, we will build 3 different models that can perform such a task. These are first principal component analysis, the most famous one, then linear discriminant analysis, and finally kernel PCA. So we will build these 3 models, one for each section, and now we're about to start with the first one, principal component analysis. But before we start, let's just make sure everyone here is on the same page. I gave you the link to this folder right before this tutorial in the article, so make sure to connect to it. And now we should be all on the same page, so we're going to go into part 9, dimensionality reduction. Alright, and as I told you, you have the 3 sections corresponding to each of the models, and we're going to start with principal component analysis, PCA. And as usual, we're going to start with Python, and in this Python folder you will find 2 files as usual. First, the implementation in IPYNB format, which now once again we will be able to run on Google Collaboratory because we will work with a classic dataset. And speaking of which, here is the dataset, wine.csv. So let's open it and let me explain what this is about. Alright, so actually first, you notice indeed that we have many features. I did not take a dataset with hundreds of features because then we would, get lost in the dataset. So I just took a dataset with more than 10 features, and of course these are all the features from here, alcohol, to this one, proline. And as you can guess, each feature gives a certain information of a certain wine, right? Each row corresponds to a wine, and for each wine we have diverse informations, diverse features, characteristics of the wine. The alcohol level, the malic acid, I'm not an expert of wines, but these are some wine's characteristics. Ash alkalinity, magnesium, total phenols, flavonoids. Anyway, so you see you have many wine features, and for each of these wines, well, there we go, I'm about to explain the dependent variable. For each of these wines, we have the customer segment, that's the last column, to which the wines belong. Okay, so let me explain what happens in terms of business. First of all, this is a dataset I took from the UCI ML repository, so all the credits go, of course, to this amazing platform of datasets. However, in this dataset, I just changed the last column, customer segment, to make it more business-wise, to make this case study more a business case study. Because the scenario is the following. Let's imagine that this dataset belongs to a wine merchant with many different bottles of wine to sell and therefore a large base of customers. And this wine shop owner actually hired you as a data scientist to first do a preliminary work of clustering, meaning that at first we had all these features without this last column, customer segment. We have all these features from alcohol to proline, and this wine shop owner actually asked you to perform some clustering to identify diverse segments of customers grouped by similarities which correspond to the wines they prefer. Alright, so each customer segment here, and by the way there are 3 of them, right? If we scroll down we can see that we have 3 different categories or clusters, and each of these segments correspond to a certain group of customers that have similar preferences for similar wines. And that's exactly what these segments are about. But that was the first work, and if you want you can have fun and do this first work yourself. But here we want to work on dimensionality reduction, so there goes the second mission that this wine shop owner asked you to do. This wine shop owner was actually satisfied with your first work, identifying these 3 segments, but now the owner would like to, reduce the complexity of this dataset by ending up with a smaller amount of features. And at the same time, this owner would like you to build a predictive model that will be trained on these data, including the features up to here and the dependent variable, so that for each new wine that this owner has in its shop, we can deploy this predictive model applied to a reduced dimensionality dataset to predict which customer segment this new wine belongs to, right? And therefore, once we manage to predict which customer segment this wine belongs to, then we can recommend this wine to the right customers. And that's exactly why what we're about to do is like a recommender system. Because for each new wine that will be in the shop, well, our predictive model will tell us to which customer segment it will be the most appropriate. It will be the most appreciated. All right, so that's the business case study, and therefore, our predictive model will add tons of value to this owner, because therefore, if this owner manages to build a good recommender system, of course, it will optimize the sales and therefore the profit of the business. Okay, so that's what the case study is about. Now we're gonna move on to the implementation, of course. Therefore, I'm opening this file, Principal Component Analysis, which you have the choice to open with either Google Collaboratory or Jupyter Notebook, as we did in the previous section on CNNs. But there we go. Let's open it with Google Collaboratory and enjoy a brand new implementation on it. All right, so here is the implementation, Principal Component Analysis. This is in read-only mode, so as usual, we will create a copy by clicking File here and then Save a Copy in Drive. This will create a copy inside which we will be able to re-implement, not the whole implementation this time, because I will explain that most of the sales are sales we already did before, many times in the classification part and also in the first section of part 8. So we won't have to re-implement everything. This would be a waste of time, and mostly we rather want to focus on dimensionality reduction. And therefore, here is what we're going to do. I'm going to show you the implementation, of course, but the only cell that we will re-implement will be this one, applying PCA. So let's remove it right away, not the text cell, only this one. And now I'm going to show you that indeed, all the cells are super familiar to us, right? Because indeed, we start by importing the libraries that we did 100 times, right? So we have the 3 essential libraries here. Then we import the dataset with the exact same code as the one you have in your data preprocessing template. So of course here I just put the right name of the dataset, which is wine.csv. Okay, then you will recognize the next steps of the data preprocessing template, which is to split the dataset into the training set and the test set, exactly the same code. Then we apply feature scaling as it is, most of the time recommended. So we apply it, of course, on separately the training set and the test set. And that closes the data preprocessing phase. Then we apply PCA, and that's, of course, the cell we will re-implement together. Then let me just remove all the outputs here so that you don't see them. I hope you closed your eyes when I just removed them. But there you go. Now close your eyes a little bit. I'm going to remove that output as well, because actually the dimensionality reduction technique that we'll use will manage to get us great results with only 2 extracted features, right? We're not reducing the number of existing features. We are creating new extracted features based on these existing features. So we will get totally different new features at the end, which we call, principal components. So we'll have principal component 1 and principal component 2 at the end. But there we go. So back to our implementation. After applying PCA, which we will redo together, we train the logistic regression model on the training set. I chose the logistic regression model as the first model of our classification toolkit, but I could have chosen any other ones, but you will see that we will get great results with this one, but feel free to choose another classification model. Any will work. But notice that it is important to apply PCA before training your classification model on the training set, right? You want to reduce the dimensionality of your data set before, of course, training it on your training set, right? The training set basically is the final version of your data after you performed all the data preprocessing phase and dimensionality reduction if you want, okay? So the training happens after applying your dimensionality reduction technique. And then, of course, we will make the confusion matrix. You know how to do that. We did it many times. And then, since our dimensionality reduction technique will get us great results with only 2 extracted features, principal component 1 and principal component 2, that will allow us to visualize the training set results in 2 dimensions, right? Because remember that each dimension corresponds to 1 feature. And we do this for the training set right here and the test set. Okay, so as you can see, what I did with this implementation is something you can do in less than 5 minutes right now thanks to your toolkit, right? Because you just need to take the data preprocessing toolkit to make these first cells. Then you just need to grab the feature scaling tool in your data preprocessing toolkit. Then you just need to grab your logistic regression implementation to implement this cell. And same for the other ones, you know, the confusion matrix. And same for these last two, visualizing the train set results and visualizing the test set results. These are all cells that you have in your logistic regression implementation. So absolutely no need to do it together again. And therefore, we can now focus directly on this cell applying PCA. So there we go. We're going to create a new code cell, and now let's implement PCA, Principal Component Analysis. All right, so you could almost press pause on the video now and get the right tool from the Scikit-learn API to see how to implement this. That would be a good exercise, but if you don't want to do it, that's fine. Let's implement this right now. And as you guess by what I've just said, well, we're going to implement PCA using the Scikit-learn library. So the first thing we'll do is start from Scikit-learn, from which we're going to get access to a certain module, which you will find in the Scikit-learn API, and which is called decomposition. Just like that, decomposition, from which we're going to import, of course, a class that will allow us to build this object, which will be nothing else than this PCA tool that will apply dimensionality reduction on our dataset. And that class is called, very simply, PCA. Okay? So you can't miss it in the API. PCA, and now the next natural step is, of course, to create an object or, an instance of this class. And guess how we're going to call that object? Well, very simply, we're going to call that object PCA, right? So this is super intuitive. And now you know the next step. The next step is to call the PCA class, which needs to take one essential argument. We only have to input one argument here, and you can totally guess what this argument will be, right? It is the final number of extracted features you want to end up with in your new dataset. And that argument, to choose that number, is called n_components. N components. All right, so now the question is, of course, which number should we choose, right? How do we know down to which number of features, right, extracted features, we want to reduce the dimensionality of our dataset? Well, I have a very simple answer to that question. What I usually do is start with two principal components, therefore two extracted features, and see the results I get in the end. And thanks to our code, our code template, we can check that very quickly and easily. And besides, we do want to try with two, because then if we get good results with two, well, we will be able to visualize the training set result and the test set result in 2 dimensions, in this nice plot that we had in part 3 classification. So we definitely want to start with 2. And if, we get really poor results and we see on the graphics here that we can't separate the 3 classes properly, remember with those different prediction regions and the prediction boundary, well, if we see that we have poor results on the visualizations, then we can try with higher numbers of principal components, meaning 3, then 4, and at some point we'll get, some extracted features that explain well enough the variance, which is exactly what PCA is about, right? It is about extracting some features that explain well enough the variance. And once you find them, well, you will get good results even with a lower dimensionality. Okay, so let's try with 2 and let's see what we'll get, but I already told you that we'll get amazing results. Therefore, there you go, n components equals 2. 2 principal components, or in other words, 2 extracted features. Okay, so that's for our object, and now the next step, of course, is to apply this object to our training set to reduce the dimensionality of our training set in order to ease the learning process of the logistic regression model. But also we will have to apply it on the test set, because remember that the predict method that we will call here has to be called on the exact same format of data as the one that was used for the training set. So as long as you apply some transformations like data preprocessing or dimensionality reduction on your training set, well, you have to do the same on your test set. However, be careful, exactly as feature scaling, we will have to apply the fit transform method on the training set, but only the transform method on the test set. And that's always for the same reason. That's because we want to avoid information leakage on the test set, right? The test set is supposed to be new observations like data on which we deploy our model in production, and therefore we're not supposed to fit our scalar or feature extractor objects on the test set. We can apply them to transform them, right? Because they were fitted on the training set, but we can't fit them again to the test set because that would be like trying to get some hints of information from the test set that we're not supposed to have. That's exactly what information leakage is about. So there you go. I said everything. Now you can press pause on this video to finish this implementation of PCA. And in 2 seconds, I'm going to implement with you the solution. All right. I hope you did well. Now let's do it together. So as we said, we want to apply this PCA object separately on the training set and test set. So first I'm going to take xtrain, all right, which I'm going to update by applying this PCA object from which I'm going to call the fit transform method on this older version of xtrain, meaning before the transformation of PCA. And so here, what happens technically is that the fit part of this fit transform method will get all the information it needs from xtrain to apply principal component analysis. And then, of course, the transform part of this fit transform method will apply the transformation itself to extract the principal component features. Okay, so that's what it means technically. And now, well, let's do the same actually for xtest. So I'm copying this, pasting it here, and replacing here xtrain by xtest, then xtrain here again by xtest, and only applying the transform method. And there we go, my friends. This implementation is already over.